Today we'll discuss middle term and the greatest binomial coefficient in binomial expansion. Now we'll come back to our Pascal's triangle. If I'll see this n equals to 1, then there are two terms. So basically there are two middle terms. If n is 2, then the middle term is second term. If n is 3, now I have 4 terms. So again I'll have two middle terms. For n equals 4, again one middle term, and that is the value is 6. For n equals to 5, again it is 10 and 10. And for n equals 6, there will be again one middle term. So from here, what we can conclude is, if n is an odd number, then there will be two middle terms. And if n is an even number, then there will be only one middle term. Now we can also see that this middle term is related to greatest binomial coefficient, because in the binomial expansion, the coefficient of the middle term, see here it's 2, which is greater than 1 and 1, 3 greater than 1 and 1, 6 greater than 4, 10 greater than 5, 20 greater than 15. So if we have to find greatest binomial coefficient, and here we are just talking about binomial coefficient, that is greatest nCn-r in any expansion. So in the expansion, we are just going to consider the value of nCn-r and no other expression with it. Now there will be some questions where we need to find numerically greatest term. Now that question is different from this question. Here we are just concerned with nCn-r, which is greatest binomial coefficient, and not the value of whole term. So if it is greatest binomial coefficient, then all I need to do is I need to find its middle term, and for that middle term I need to find its binomial coefficient. Now how do we do that? Now we know that when n is even, in that case there is only one middle term. So here the value of r is given by simply n by 2, and the term will be simply t n by 2 plus 1. So there will be only one middle term, and that middle term is given by t n by 2 plus 1. Now when n is odd, in that case there will be two middle terms. So 1 and 1, 3 and 3, 10 and 10. So in that case the value of r is given by either the value of r is, so one of the value of r is n minus 1 by 2, and the other value of r is n plus 1 by 2. So here there will be two middle terms. So n minus 1 by 2 plus 1, and then t n plus 1 by 2, and then plus 1. So if the question is find the middle term in a binomial expansion, or the question is find the term having greatest binomial coefficient, then all I need to do is, if the value of n is even, I'll take r as n by 2, and if n is odd, I'll take r as n minus 1 by 2 and n plus 1 by 2. So say for example, if the value of n is 6, then the value of r is given by 6 by 2, which is 3. And in that case, the term is fourth term. So 1, 2, 3 and 4. So that's your middle term. And if n is odd, which is 5, then r is 5 minus 1 by 2, which is 2. Or r is n plus 1 by 2, which is 3. So in that case, the term will be third term and fourth term. So 1, 2, so that's your third term, and that's your fourth term. So this is how we find middle term, or the term with greatest binomial coefficient in binomial expansions. In the coefficient of middle term, in the expansion of 1 plus alpha x to the power 4 and 1 minus alpha x to the power 6 is same, then we need to find the value of alpha. Now we need to find middle term in this. Now for this expansion, the value of n is 4, which is an even number. So in that case, the value of r will be given by simply 4 by 2, and which will be 2. So there will be third term. So this term will be given by t3, and it will be 4c2 1 to the power 4 minus 2 and alpha x whole square. So this is 4c2 alpha square into x square. Now for the second series, here the value of n is 6, which again is an even number. So again the value of r here will be n by 2. So it will be 6 by 2. So there will be 3. So now the term here is fourth term, and that term is given by 6c3 1 to the power 6 minus 3 and minus alpha x to the power 3. Now it is 6c3, and here will be minus alpha cube into x cube. Now here it says the coefficient of the middle term. It doesn't say binomial coefficient. It says general coefficient of middle term. So that is the coefficient in the first case is 4c2 alpha square, and the second case it is 6c2 into minus alpha cube. So they are equal. So if I'll equate them, I'll write 4c2 into alpha square and minus 6c3 into alpha cube. Now what is 4c2? 4c2 is 6 and 6c3 will be 20 alpha cube. So I'll cancel it. So I'll get the value of alpha as minus 3 by 10. Here the question is, find the numerical value of the middle term in the expansion of 1 minus 1 by x to the power n into 1 minus x to the power n. So what I'll do is, I'll multiply these two expressions. If I'll multiply them, I'll write 1 minus 1 upon x minus x plus 1 whole to the power n. Now I can write it as minus x minus 1 upon x and then plus 2 to the power n. So I'll take minus common. So if I take minus common, I'll write minus 1 to the power n. And here I can write x plus 1 upon x minus 2 to the power n. So I can also write it as under root x whole square plus 1 upon under root x square minus 2 whole to the power n. Now this is a square plus b square minus 2ab, which is minus 1 to the power n, and this is under root x minus 1 upon under root x whole square, and this square and n, so it will be 2n. Now, which is a binomial expansion. So for this binomial expansion, I'll need to find the numerical value of its middle term. So this minus 1 to the power n, so you'll get multiplied, and then its middle term will be given by, now since n is even, which is 2n, so value of r will be 2n by 2, which is simply n. So there will be tn plus 1th term, and its coefficient will be given by 2 nCn under root x, 2n minus n will be n, and then minus 1 upon under root x to the power n, so it will get cancelled. So this is minus 1 to the power n into minus 1 to the power n, which is simply plus 1. So answer to this question simply will be 2 nCn. So the numerical value of the middle term in this expansion will be 2 nCn. In the previous video, we have discussed greatest binomial coefficient and middle term. Now in this video, we want to discuss numerically greatest term. Now numerically greatest term, it's different from greatest binomial coefficient, because in binomial coefficient we'll just discuss the value of nCn. But for numerically greatest term, we'll have to consider the value of nCn as well as the values of x and a. Now how do we solve such questions? So what I'll do is, if I'll say, suppose in my expansion there is a term and which is numerically greatest term, then in that case tr plus 1, suppose this term is numerically greatest term, so I'll put a mod sign, and this term, it should be greater than its rth term, and it should also be greater than its r plus 2th term. And if there is any term which satisfies this condition, then I'll say tr plus 1th term will be my numerically greatest term. Now how do we simplify it? So what I'll do is, I'll consider the value of mod of tr plus 1, and it should be greater than, or maybe at times I may get an equality sign because two terms may have same value, should be greater than mod of tr, and we want to simplify this condition. So I can also write it as mod of tr plus 1 upon tr, and it should be greater than or equal to 1. Now what is tr plus 1? So it will be nCr x to the power n minus r, a to the power r, and here it will be nCr minus 1 x to the power n minus r plus 1, a to the power r minus 1, and it should be greater than or equal to 1. Now n is same, r differs by 1, so I can write it as n minus r plus 1 upon r, and here the value of x will cancel, value of a should also cancel, so here I'll get a and here I'll get x, so I can write a upon x, and it should be greater than or equal to 1. So now I know this expression is positive, so I can write it as n plus 1 minus r upon r, and this is mod of a upon x should be greater than or equal to 1. So I'll take it on the right hand side, so I can write it as n plus 1 upon r minus 1 should be greater than or equal to mod of x upon a, and if I'll take it on the right hand side, I can simply write it as n plus 1 upon r, and it should be greater than 1 plus mod of x upon a. So I'll find r from this, then the value of r should be r should be less than or equal to n plus 1 upon 1 plus mod of x upon a. So I've got an expression or a condition which says tr plus 1 will be greater than or equal to tr when the value of r is less than or equal to n plus 1 upon 1 plus mod of x by a. Now we have two separate cases. Case 1, when n plus 1 upon 1 plus mod x upon a, suppose it's an integer. So now in this case, I'll say suppose this value is equal to some number n. So for this condition, I'll take three separate cases. Case 1, when the value of r is less than m. Case 2, when the value of r is equal to m. And the third case, when the value of r is greater than m. Now, when the value of r is less than m, so in that case, if I'll take this condition, then I can simply say t1 is less than t2, t2 is less than t3, and it will continue up to value of r should be m minus 1. If it continues up to m minus 1, then the condition I'll get is tm minus 1 is less than tm. Now, when the value of r is equal to m, so there I'll get this equality sign. Now, when I'll get this equality sign, so from here I can say this tm is equal to tm plus 1. So, these two terms will have same value. And when r is greater than m, so it'll be a opposite condition. So, in that case, it'll be tm plus 1 because it starts with the value greater than m. So, tm plus 1 should be greater than tm plus 2. Tm plus 2 should be greater than tm plus 3. So, we'll go on. So, in this case, when n plus 1 upon 1 plus mod x upon a is an integer, say m. So, in this case, there will be two numerically greatest terms. So, there will be two numerically greatest terms, and those terms will be nth term and m plus 1th term. Now, for the second case, when n plus 1 upon 1 plus mod x upon a is some number m, which is not an integer. So, again, we'll have two separate cases. So, here we'll have first case when the value of r is less than m, and the second case when the value of r is greater than m. Now, when the value of r is less than m, now this condition holds, right? So, I'll get t1 is less than t2, t2 is less than t3. So, now what is the largest integral value which is just close to m? So, in that case, the value of r simply will be greatest integer function of m. So, here I will write t greatest integer function of m should be less than t greatest integer function of m plus 1. Now, when r is greater than m, so it will be the opposite condition. So, for the opposite condition, if I take r greater than m, then the value of m here will be greatest integer function of m plus 1. So, in that case, I will write t times greatest integer function of m plus 2 is less than t greatest integer function of m plus 1. Greater function of t m plus 3 is less than t greater function of m plus 2. So, we'll continue in this way. So, here we'll have only one numerically greatest term, and that numerically greatest term will be t greatest integer function of m plus 1. So, this is how we simplify conditions for numerically greatest term. Now, every time when I want to calculate numerically greatest term, I do not wish to go through all these cases. So, what I'll do is I'll create a shortcut, and the shortcut will be, suppose if I have to find numerically greatest term in the expansion of x plus a to the power n, then simply I'll find this value, which is n plus 1 upon 1 plus mod of x upon a, and I'll say this value is equal to some number n. Now, depending on this m, if n is an integer, then in that case, there will be two numerically greatest term, and there will be its nth term and m plus 1th term. And if m is not an integer, in that case, there will be only one term, and that numerically greatest term will be t greatest integer function of m plus 1th term. So, this is how we are going to solve the questions for numerically greatest term. Now, every time when I want to calculate numerically greatest term, I do not wish to go through all these cases. So, what I'll do is I'll create a shortcut, and the shortcut will be, suppose if I have to find numerically greatest term in the expansion of x plus a to the power n, then simply I'll find this value, which is n plus 1 upon 1 plus mod of x upon a, and I'll say this value is equal to some number n. Now, depending on this m, If n is an integer, then in that case there will be two numerically greatest term, and there will be its nth term and m plus 1th term. And if m is not an integer, then in that case there will be only one term, and that numerically greatest term will be t greatest integer function of m plus 1th term. So this is how we are going to solve the questions for numerically greatest term. So let us take up a question which says find the numerically greatest term in the expansion of 3 minus 5x to the power 11 when the value of x is 1 by 5. So we'll solve this question using shortcut. So what I know is we have to compare it with the expansion x plus a to the power n, and then I'll find the value of m, which is n plus 1 upon 1 plus mod of x upon a. Now x in this case is 3, a is minus 5x, and the value of n is 11. So if I'll put it, I'll get n is 11, so it is 11 plus 1, and it is 1 plus mod of, what is the value of x? X here is 3. And what is the value of a? A is minus 5x. Minus 5, and then I'll put the value of x also. So value of x is 1 by 5. So 5 and 5 will cancel. So I'll get this value as 11 plus 1 upon 1 plus 3, which is 12 by 4, which is 3. So from here, the value of m that I'm getting is m is equal to 3, which is an integer. Now we know that if m is an integer, then in that case, there'll be two numerically greatest terms, and those terms will be either nth term or m plus 1th term. So in this case, when the value of m is 3, so the numerically greatest term will be either its third term or its fourth term. So I'll find third term. So if I'll find its third term, so third term will simply be, so for third term, value of r is 2. So there'll be 11c2 minus 3 to the power 11 minus 2 minus 5x to the power 2. Again, I'll put x as 1 by 5. So this value will be 1. So 11c2 is 55, and there will be 3 to the power 9. Now for the fourth term, I'll put the value of r as 3. So if I'll put r as 3, I'll get 11c3, 3 to the power 11 minus 3, minus 5x to the power 3. So 5x again will be 1, and this is minus 1, 3 will be minus. So it will be minus 11c3, and then it will be 3 to the power 8. Now if I'll simplify 11c3, it simplifies to minus 55 into 3, and this is 3 to the power 8. So again it will be minus 55 into 3 to the power 9. So numerical value of third term is same as numerical value of its fourth term. So the numerically greatest term in the expansion of 3 minus 5x to the power 11 when x is 1 by 5 is either third term or its fourth term. So now we'll try and solve this question using the shortcut. Now for shortcut, we'll find the value of m, and the value of m simply will be n plus 1, and n plus 1 in this case is 2n plus 1 upon 1 plus mod of x. Now x in this case is 1, right? So 1 upon x, and this value, it should give me the greatest term, and this greatest term should be its middle term. So for this middle term, r equals 2n by 2, and there will be simply n. So its middle term will be t n plus 1. Now if this term is also the numerically greatest term, it should not be an integer, and the numerically greatest term will be given by t greatest integer function of m plus 1, and this t greater function of m plus 1 should be equals to t n plus 1. So from here I can say the value of greatest integer function of m, it should be equals to n. Now greater function of m is equal to n. Now in that case, the value of m should lie between n and n plus 1. And now because m is not an integer, so I won't have this equality sign. So I'll get this condition, which is the value of m should lie between n and n plus 1. So here it is n. Now what is the value of m? Value of m simply will be 2n plus 1 upon 1 plus x, and it should be less than n plus 1. So if I take the reciprocal, then sign will reverse, right? So I'll write 1 upon n should be greater than 1 plus 1 upon x should be greater than 2n plus 1 should be greater than 1 upon n plus 1. So I'll multiply 2n plus 1. So I'll write 2n plus 1 by n should be greater than 1 plus 1 upon x should be greater than 2n plus 1 upon n plus 1. Now I'll subtract 1 also. So if I'll subtract 1, I'll write n plus 1 upon n should be greater than 1 upon x, and it should be greater than n upon n plus 1. Now I need to find the value of x. So again, I'll take the reciprocal. And both the numbers, they are positive. So if I take the reciprocal, I'll write n upon n plus 1 is less than x is less than n plus 1 upon n. So we can solve it using traditional method, and we can also solve it using shortcut method also. In this case, we have assumed m is not an integer, considering that there is only one numerically greatest term, and that one numerically greatest term will be its middle term. If I'll consider this m as an integer, then I'll end up having two separate values. Now let us take up another question which says, if the middle term in the expansion of 1 plus x to the power 2n is the greatest term, then prove that the value of x should lie between n upon n plus 1 and n plus 1 upon n. So now what I know is it's an even power. Now in case of an even power, the value of r is given by 2n by 2. So there'll be n. So its middle term will be tn plus 1th term. And this term, if it is numerically greatest term, then tn plus 1 should be greater than tn, and it should also be greater than tn plus 2. Now if I write tnth term, so tnth term will be 2ncn minus 1 x to the power n minus 1, and it should be less than 2ncn x to the power n, and it should be greater than 2nc n plus 1 and x to the power n plus 1. Now first I'll simplify these two expressions. So here x and x will cancel, so I can write x should be greater than twice ncn minus 1 upon twice ncn. Now n is same, r differs by 1, and this is greater, so I'll write it as n minus r plus 1 upon r. So this value will be n upon n plus 1. So here the condition I'll get is the value of x should be greater than n upon n plus 1. Now if I take these two conditions, so here again x will cancel, so I'll get x should be less than 2ncn upon 2n cn plus 1. Now here again r n is same, r differs by 1, and this is greater, so I'll write x is less than n minus r plus 1 upon r. So x should be less than, so there's n plus 1, and here 1 and 1 will cancel, so I'll get n plus 1 upon n. So combining or considering the two conditions, I'll get the value of x as the value of x should be greater than n upon n plus 1, but it should be less than n plus 1 upon n. So this is how we can prove the value of x should lie between n plus 1 upon n plus 1 and n plus 1 upon n. So in this video, we'll discuss a very interesting and important formula, which is Legendre's formula, also known as de Broglie formula. So the formula says, suppose I have factorial n, and I know I can express any number as any prime powers like 2 to the power a, 3 to the power b, 5 to the power c, and suppose I have any prime number p, and I need to find what is the exponent of prime number p in factorial n. So when we need to find exponent of any prime number in a given factorial, then we'll use Legendre's formula or de Broglie's formula. So the formula says the exponent of prime number p in factorial n is given by greatest integral function of n upon p, greatest integral function of n upon p square, greatest integral function of n upon p cube, and we'll continue, and after some time this n upon p to the power r will be less than 1. So in all such successive cases, in that case and plus all successive cases, its value will be 0. So we'll have restricted number of cases. Say for example, suppose I have factorial 5, and factorial 5 as we know is 120. 2 cube into 3 into 5. Now suppose I want to find exponent of 2 in factorial 5. So it will be given by 5 upon 2, 5 upon 2 square, 5 upon 2 cube. So 5 by 2 is 2.5, 5 by 4 is 1.25, and then this value will be less than 1. So all successive values will be 0. So greatest needed function of 2.5 is 2 and greatest needed function of 1.25 is 1. So the exponent of 2 in factorial 5 will be 3. So we'll use this formula to find exponent of some prime number p in factorial n. Now how do we use this formula? So what are the questions that we are likely to get in this? So let us take up another question which says find the number of zeros at the end of factorial 108. Now what I know is, again I can write factorial 108 as sum 2 to the power a, 3 to the power b and 5 to the power c, and when this 2 gets multiplied with 5, I'll get this value as 10. So if I have to find number of zeros at the end of 108 factorial, then I have to find exponent of 2 and I'll also have to find exponent of 5. So if I have to find exponent of 2 in factorial 108, so what I'll do is I'll write 108 by 2, 108 by 2 square, 108 by 2 cube, 108 by 2 to the power 4, 108 2 to the power 5, 108 2 to the power 6, 108 2 to the power 7, I'll go on. Now this is 54, this is 27, 13.5, 6.75, 3.375, 1, 6, 8, 7, 5, and then it'll be 0.8 something. So after this, it'll all be 0. So I'll simply write it as 54 plus 27 plus 13 plus 6 plus 3 and plus 1. So which is 104. 10 and that is 40. So 50, 50 and 54 is 104. Now we'll find exponent of 5. So exponent of 5 in factorial 108. So there'll be 108 by 5, 108 by 5 square and 108 by 5 cube. So there'll be 21.6 and then 21.6 divided by 5, 4.72 and then all the values will be 0. So there'll be 21 plus 4. So there'll be 25. So in this 108 factorial, I'll have 2 to the power 104 and then I'll also have 5 to the power 25 because the number of 5 is limited. So 25 times this 5 gets multiplied with 2. So I'll get 10 to the power 25. So in the end, there'll be 25 zeros in factorial 108, or there'll be 25 zeros at the end of factorial 108. So the question is find the exponent of 7 and 100C 50. Now what I know is 100C 50 is actually factorial 100 factorial 50 into factorial 50. So what I'll do is I'll find exponent of 7 in factorial 100 and I'll also find exponent of 7 in factorial 50. So for factorial 100 will be 100 by 7, 100 by 7 square, 100 by 7 cube. I'll go on. Now 100 by 7 is nearly 14.28 something. Then this is 2.4 something, and then this value, it is less than 1, so then it will be 0. So it will simply be 14 plus 2, that is 16. So exponent of 7 in factorial 100 is 16. So I can write it as, so it will have 7 to the power 16 in the numerator. Now what about exponent of 7 in factorial 50? In factorial 50 I can write it as 50 by 7, 50 by 7 square, 50 by 7 cube, it will go on. Now this is 7 point something, so this is 7. Now 50 by 49 is simply 1, and then all of the values they'll be 0. So this is simply 8. So the exponent of 7 factorial 50 is 8. So here I'll have 7 to the power 8, and here also I'll have 7 to the power 8. So basically 7 to the power 16 will get cancelled with 7 to the power 8 and 7 to the power 8. So in 100 C50 there will be no exponent of 7. So exponent of 7 in 100 C50 will be simply 0. Now there will be questions in binomial theorem where we need to use greatest integer function and fractional part function to solve certain problems. Say for example, a question is given as x equals 8 plus 3 root 7 to the power n, where n is a natural number, and this box represent greatest integer function. So it says prove that the integer part of this binomial expression is an odd integer, and also we need to find the value of x minus x square plus x into greatest integer function of x. Now here what I'll do is I'll take this x common. So if I'll take x common, I can write x, and it is 1 minus, I'll take minus also common. So this is x minus greatest integer function of x. So x minus greater function of x is nothing but its fraction part of x. So I need to find x into 1 minus fractional part of x. Now in this question we have both greatest integer function as well as fractional part function. So what do we do in this question is I'll write this 8 plus 3 root 7 as greatest integer function of x plus fractional part of x, and I'll write fractional part of x as f. Now I know that in this case the value of f will lie between 0 and 1 because it's not an integer. So this value it will always have some fractional part, and which will be between 0 and 1. Now I'll take up another binomial expression which is the conjugate of this expression. So I'll write 8 minus 3 root 7 to the power n, and I'll say this value is f. Now make sure when we are taking this conjugate of the given expression, this value 8 minus 3 root 7 to the power n, it should always lie between 0 and 1. Now we know that 8 plus 3 root 7 into 8 minus 3 root 7 is equal to 1. Now 8 minus 3 root 7 is 1 upon 8 plus 3 root 7. So this value is less than 1. So I can say that the value of capital F will lie between 0 and 1. So now if I'll expand these two series, I can write from the first one, I can write greatest integer function of x plus f is nc0 a to the power n, nc1 a to the power n minus 1 3 under root 7, nc2 a to the power n minus 2 3 root 7 whole square, and from the second series I can write f is nc0 a to the power n minus nc1 a to the power n minus 1 3 root 7 plus nc2 a to the power n minus 2 3 root 7 whole square. Now from these two series I need to cancel out the terms having under root sign. So in this case, if I'm going to add the two series, then these terms containing square root, they'll get cancelled. So I'll add them up. So if I'll add them up, I'll write greater function of x plus small f plus capital F, there'll be. So here this term will cancel. So I'll get 2 times nc0 a to the power n, nc2 a to the power n minus 2 into 3 under root 7 whole square. So whenever I have this irrational part, I'm having an even part. So this expression on the right hand side, it is nothing but an even integer. Now what about f plus f? What I know is the value of f lies between 0 and 1. Value of capital F also will lie between 0 and 1. So if I add them up, from here I can say the value of f plus f will lie between 0 and 2. Now greatest integer function of x, it is an integer. Right hand side is also an integer. So it simply means the value of this f plus f, it should also be an integer. So the only integral value possible in this case is 1. So from here I can say value of f plus capital F it should be 1. So that is greatest integer function of x plus 1. It should be an even integer. That is greatest integer function of x should be even integer minus 1. So there will be an odd integer. So from here we can say the greatest integer part for this given binomial expression is an odd integer. Now if I look at the second part is simply I need to find the value of x into 1 minus fraction part of x. So this is x into 1 minus, and we have taken this fraction part as f. So 1 minus f. So this is x, and what I know is f plus f is 1. So 1 minus small f is capital F. So it is x into capital F. What is x? X is 8 plus 3 under root 7 to the power n. And what is capital F? Capital F is 8 minus 3 under root 7 to the power n. So if I'll multiply them, I'll get what? 64 minus 63 to the power n, which is 1. So answer to the second part is 1. So the value of this expression is nothing but 1. So let us take up another question, which is find the value of 3 plus under root 5 to the power 5, its greatest integer function. So I need to find integral value of this given binomial expression. So what I'll again do is, I'll write this as the greatest integer function of x plus small f as 3 plus under root 5 to the power 5. Now the value of f will always lie between 0 and 1. And now I'll take its conjugate. So its conjugate will be 3 minus under root 5 to the power 5. Root 5 is 2.2 something. So this value is less than 1. And any number which is less than 1 raised to the power 5 will also be less than 1. So the value of f will also lie between 0 and 1. So now I'll expand the given two binomial series. So I'll write greatest integer function of x plus f as 5c0 3 to the power 5 root 5 to the power 0 5c1 3 to the power 4 root 5 to the power 1 5c2 3 to the power 3 under root 5 square and 5c5 3 to the power 0 under root 5 to the power 5, and the next one will be capital F, which is 5c0 3 to the power 5 under root 5 to the power 0 minus 5c1 3 to the power 4 under root 5 plus 5c2 3 to the power 3 under root 5 square, and then finally it will be minus 5c5 3 to the power 0 under root 5 to the power 5. Now again I need to cancel the terms which contains square root. So I'll add them up. So I'll write greater function of f plus f, and this is 2 times 5c0 3 to the power 5 5c2 3 cube under root 5 square and plus 5c4 3 to the power 1 under root 5 to the power 4. So now I know that the value of f lies between 0 and 1 and value of capital F also lies between 0 and 1. So the value of small f plus capital F will lie between 0 and 2. So I can write it as this is greatest integer function of x plus f, and this is 2 times. Now 3 to the power 5 will be 243, and this one will be 1350, and here will be 375. So if I'll multiply them, I'll get this value as 3936. Now greater function of x, it's an integer. 3936 is also an integer. Now what about f plus f? So it will also be an integer. So the only integral value possible in this case is value of f plus f, it should be 1. So if I'll put this value here, I'll get greatest integer function of x plus 1 is 3936. So the value of greatest integer function of x is 3935. So the value of greatest integer function of 3 to the power root 5 to the power 5 is 3935. Now we'll take another question, which is r equals 5 root 3 plus 8 to the power 2n plus 1, where f is r minus greatest integer function of r. I need to find the value of r into f. So again what I'll do is I'll write this as greatest function of r plus f, and this is 5 root 3 plus 8 to the power 2n plus 1, and I'll write the binomial expansion, so which is 2n plus 1 c0, 5 root 3 to the power 2n plus 1, 8 to the power 0, 2n plus 1 c1, 5 root 3 to the power 2n, 8 to the power 1, and it will go on. And I'll also take its conjugate. So now its conjugate will be 5 root 3 minus 8 to the power 2n plus 1. 5 root 3 minus 8. Now 5 root 3 minus 8, this value is less than 1. So from here I can say the value of capital F will lie between 0 and 1. And we also know value of small f will also lie between 0 and 1. So if I'll expand it, I'll write 2n plus 1 c0, 5 root 3 to the power 2n plus 1, 8 to the power 0 minus 2n plus 1 c1, 5 root 3 to the power 2n into 8. So now again I need to cancel terms containing a square root. Now terms containing square root is 5 root 3 because it's an odd power. Then will be the third term. So all I need to do in this case is I need to subtract them. So previously we have added them to cancel out square root parts. Now we'll subtract them. So if I'll subtract it, I'll get r plus f minus f, and there'll be 2n plus 1 c1, 5 root 3 to the power 2n, 8 to the power 1, 2n plus 1 c3, 5 root 3 to the power 2n minus 2. There will be 8 cubed. So now in each of this expression, it is an even power on the square root expression. So it is nothing but an even integer. So capital R plus f minus f. Now capital R, it's an integer. Right hand side is also an integer. So that means f minus f will also be an integer. But both the numbers, they lie between 0 and 1. So the only integral value possible in this case is the value of f minus f should be 0. So that is small f should be equals to capital F. Now I need to find the value of r into f. Now small f is same as capital F. So there will be r into capital F. Now value of r is 5 root 3 plus 8 to the power 2n plus 1, and capital F is 5 root 3 minus 8 to the power 2n plus 1. So there will be 5 root 3 whole square. So that should be 75 minus 64 to the power 2n plus 1. So answer to this question will be 11 to the power 2n plus 1. So in this case, r will be an even integer. So greater function of r will be an even integer, and the value of r into f will be 11 to the power 2n plus 1. Now one of the use of binomial theorem is to compare the two numbers. Now say for example, a question is given as which is larger. One of the number is 1.01 to the power 1,000,000, and then another number is 10,000. So what I'll do is I'll take up the first number and I can write it as 1 plus 0.01 to the power 1 million. Now I can use binomial theorem in that. So it is 1 plus x to the power n. So I'll write first few terms. So it'll be 1 plus n. N is 1 million into 0.01, and then 1 million C2 0.01 square, and we'll continue. Now if I'll multiply 0.01 with 1 million, I'll get 1, and then I'm left with this 10,000, and then plus 1 million C2 0.01 square. So here in that case, I'll get a number which is greater than 10,000 because it is 10,000 plus something. So I can directly say 1.01 to the power 1 million is greater than 10,000. Show that 101 to the power 50 is greater than 100 to the power 50 plus 99 to the power 50. So what I'll do is I'll write the binomial expansion of 101 to the power 50. I can write it as 100 plus 1 to the power 50. So it will be 50 C0, 100 to the power 50, 50 C1, 100 to the power 49, 50 C2, 100 to the power 48, and I'll continue up to 50c 50. Now I'll also write the binomial expansion for 99 to the power 50. So it is 99 to the power 50. So it will be simply 100 minus 1 to the power 50. So that is 50c0. 100 to the power 50 minus 50c1. 100 to the power 49 plus 50c2. 100 to the power 48 and then plus 50c50. Now what I'll do is I'll subtract the second series from the first. I can write it as 101 to the power 50 minus 99 to the power 50. Now these terms, they'll get cancelled. So I'll write 2 times 50c1 into 100 to the power 49 plus 50c3 100 to the power 47. I'll continue. So I'll multiply this 2 inside. So this is 2. And then 50c1 is simply 50. And that is 100 to the power 49. This is 2 into 50c3. 100 to the power 47. And other terms. So this is 100 into 100 to the power 49. So it will be 100 to the power 50. And then plus other positive terms. Now these other positive terms plus 100 to the power 50 should be greater than 100 to the power 50. So from here I can say 101 to the power 50 minus 99 to the power 50 is greater than 100 to the power 50. So if I take it on the right hand side, I can simply say 101 to the power 50 is greater than 100 to the power 50 plus 99 to the power 50. So that's your answer. The question is, if an is 1 plus 1 by n to the power n, then we need to prove that the value of this an will lie between 2 and 3 for all natural numbers which are 2 or greater than 2. And the second part, we have to prove that if n is a natural number and n is greater than or equal to 3, then n to the power n plus 1 is simply greater than n plus 1 to the power n. Now we'll take the first part. So I write this an and I can write it as 1 plus 1 by n to the power n. Now if I use binomial theorem, I can simply write it as nc0 nc1 into 1 by n, nc2 into 1 by n square, nc3 into 1 by n cube, and it will go up to nCn and 1 by n to the power n. Now nc0 is simply 1. Now nc1 is n and it will be 1 by n. nc2 is n minus 1 upon factorial 2, 1 upon n square, n minus 1, n minus 2 upon factorial 3 upon n cube. I'll continue up to 1 upon n to the power n. Now here n and n will cancel. So I'll write 1 plus 1, which is 2, 2 plus, and I'll divide it by n square. So here will be 1 and here will be 1 upon 1 minus 1 by n and divide by 2. Here will be 1 minus 1 by n, 1 minus 2 by n, and here will be factorial 3 and will continue up to 1 upon n to the power n. Now clearly I know all these terms, they will be positive. So it will be 2 plus some positive number. So that means simply I can say that this value of an should be greater than 2. Now for the second part, we have to prove the value of this an should be less than 3. So what I know is, I'll take up this term and I'll say 1 upon 1 minus 1 upon n by 2. It is less than 1 by 2. Because this number is 1 minus something. So this value is less than 1. So this value will be less than 1 by 2. Now what about this one? 1 minus 1 upon n and 1 minus 2 upon n divided by factorial 3. Now 1 minus 1 upon n, 1 minus 2 upon n will be less than 1, and then factorial 3 is greater than 2 square. 1 upon factorial 3 will be less than 1 upon 2 square. So simply it will be less than 2 square. In the same way, third one, it should be less than 1 upon 2 to the power 8. So simply what I know is, I can write this series should be less than 2 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube up to 1 upon 2 to the power n. Now this series will also be less than 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube. So if I take infinite terms, so if I'll add more terms to it, then it will still be less. So I can say this an should be less than 2 plus, now it's an infinite GP. First term is A, which is 1 by 2 upon 1 minus R. Value of R is again 1 by 2. So this value is 3. So from here we can say the value of AN should be less than 3. So combining the two given conditions, I can simply say the value of this AN will lie between 2 and 3. Now coming to the second part, we have already established that 1 plus 1 upon n to the power n is less than 3. Now I can write n plus 1 upon n to the power n is less than 3. Now this n is greater than or equal to 3. So I can say this is less than or equal to n. So if I'll simplify it here, so I can simply write n plus 1 upon n to the power n should be less than n. If I multiply this n here, I can write n plus 1 to the power n is less than n to the power n plus 1, which is my second part. N to the power n plus 1 should be greater than n plus 1 to the power n. Now, one of the problems where binomial theorem is generally used is divisibility problem. Say for example, suppose the question is for a positive integer n, we have to prove that 2 to the power 3n plus 3 minus 7n minus 8 is divisible by 49. So what I'll do is, I'll write it as 2 cube to the power n plus 1 minus 7n minus 8. Now 2 cube is 8 and this is n plus 1 minus 7n minus 8. Now I can write this 8 as 1 plus 7 to the power n plus 1 minus 7n minus 8. Now I'll use binomial theorem. So if I'll use binomial theorem, I'll write this is 1 and this is n plus 1 into 7, and then n plus 1 c2 into 7 square, n plus 1 c3 into 7 cube, and I'll go up to n plus 1 cn plus 1 into 7 to the power n plus 1, and then we'll have minus 7n and then minus 8. Now if I'll consider this 7n and 7n, it will cancel, and then 1 and 7, it is plus 8, and plus 8 and minus 8 will also cancel. So what I'm left with is this expression. Now here what I can do is I can take 7 square common. So if I take 7 square common, so which is 49, I get n plus 1 c2 c3 into 7, and then n plus 1 cn plus 1 7 to the power n minus 1, so which is 49 into some integral value. So I can say this number is clearly divisible by 49. So let us take up another question, which is show that 6 to the power n plus 2 plus 7 to the power 2n plus 1 is divisible by 43 for all n belongs to n. So what I'll do is I'll try and change it somehow in terms of 43. So I cannot do anything about 6n plus 2, so I'll write 6n plus 2, and here I can write it as 7 into 7 to the power 2n, which is 7 squared to the power n. So I can write it as 6 to the power n plus 2 plus 7, and this is 49 to the power n. Now what I'll do is I'll write this 49 as 43 plus 6. So I'll write 6 to the power n plus 2 and then 7, and this is 6 plus 43 to the power n. Now I'll use binomial expansion. So if I'll use binomial expansion, I can write 6 to the power n plus 2 plus 7, and this is nc0 6 to the power n plus nc1 6 to the power n minus 1 into 43, nc2 6 to the power n minus 2 into 43 square, and all other terms. Now I'll consider these two terms. So I can write it as 6 to the power n into 36, and this is 7 into 6 to the power n, and for all these terms I can take 43 common. So it will be 43, and then nc1 6 to the power n minus 1, nc2 6 to the power n minus 2 into 43. So all these terms, they are multiple of 43. Now what about this one? 36 plus 7, which again is 43. So this is 43 into 6 to the power n plus 43 into some integer k. So I can take 43 common. So this is 43 and 6 to the power n plus k. So this number is a multiple of 43, and hence it is divisible by 43. Now we want to figure out if there is some sort of shortcut for divisibility problems. So the question is same, 6 to the power n plus 2 plus 7 to the power 2n plus 1 is divisible by 43, and we have to prove that, right? So in order to show that this number is divisible by 43, so I have to express either both or at least one of the number as some multiple of 43 or some number closer to 43. So what I know is 7 square is simply 49 and 49 minus 6 is 43. So I'm going to write it as 6 to the power n plus 2 and then I write 7 to the power 2n into 7. So this is 6 to the power n plus 2 and then I write the 7 first and then 7 square is 49 to the power n. So I write 6 to the power n plus 2 plus 7 and this is 43 plus 6 to the power n. Now this number 43, we have to look for the multiples of 43. So all the terms containing 43 or any higher power of 43, they'll be divisible by 43. So I have no interest in them. So what I'll do is, I'll simply discard this term and I'll write the shortcut as 6n plus 2 plus 7 into 6 to the power n and then plus some terms which are multiple of 43. So which I'll get from the expression. So this is 6 to the power n into 6 square plus 7 into 6 to the power n plus 43k. So it will be 6 to the power n and 36 plus 7 is simply 43 plus 43k. So this number is clearly divisible by 43. Now in all the subsequent questions, I'll not write this 43k because I know all these expressions, they'll be divisible by 43. So I'll simply write 6 to the power n plus 2 and then 7. This is 43 plus 6 to the power n. So I'll just write 6 to the power n into 6 square, 7 into 6 to the power n. I won't write this 43k every time. So this is how we are going to use shortcut for divisibility problems. Now for these problems, there is a direct shortcut also. So other way of doing it can be, I'm going to write it as 6 to the power n plus 2 and then 7 into 7 to the power 2n. So it will be 6 to the power n plus 2 and 7. And here I'll write 49 to the power n, 6 to the power n plus 2 and 7. So I need to express this 49 in terms of 43. So I'll write 6 plus 43 to the power n. Now, if I have to divide it by 43, then all of the number will be a multiple of 43. Then all I'm left with is 6 to the power n plus 2 plus 7 into 6 to the power n. So this will be 36 into 6 to the power n plus 7 into 6 to the power n, which again will be 43 into 6 to the power n, which again is divisible by 43. So one of the shortcut is you have to express that number or binomial factor in terms of the number in which we want to discuss its divisibility. Now let us take up another question, which is find the remainder when 8 to the power 2n minus 62 to the power 2n plus 1 is divisible by 9. Now I have to check divisibility by 9. So what I need to do is I need to express these numbers as some multiple of 9. So what I know is I can simply write 8 as 9 minus 1 to the power 2n and then minus. Now a multiple of 9 which is close to 62 is 63. So I can write 7 into 9 minus 1 to the power 2n plus 1. Now because we are discussing divisibility by 9, so I'll discard this 9. I'll also discard 9 into 7. So I can simply write it as minus 1 to the power 2n and then minus 1 to the power 2n plus 1. Now minus 1 to the power 2n is 1 and minus 1 to the power 2n plus 1 will be minus 1. So minus and minus will be plus. So this is 2. So the remainder when this expression is divided by 9 will simply be 2. So this is how we use this shortcut. So another question is, show that 1 to the power 1997 plus 2 to the power 1997 up to 1996 to the power 1997 is divisible by 1997. Now because we have to discuss divisibility by 1997, so I have to express these numbers in terms of 1997. So what I'll do is, I'll pair these numbers. I'll pair the first one with the last one, second one with the second last, third one with the third last, and because there are even number of terms, so each and every number will be paired with some other number. So I'll write it as 1 to the power 1997 plus 1996 to the power 1997, 2 to the power 1997 plus 1995 to the power 1997, 3 to the power 1997 plus 1994 to the power 1997, and we'll continue. Now I can write this as 1 to the power 1997 plus, and I'll express this number in terms of 1997. So I'll write 1997 minus 1 to the power 1997. In the same way for the second one, I'll write 1997, and this is 1997 minus 2 to the power 1997. Same way for the third one. Now, using the shortcut, so this is 1997, and here every term will be a multiple of 1997 except for the first term. So I'll use the shortcut and I'll simply write it as minus 1 to the power 1997 plus all other terms which are multiple of 1997. In the same way for the second one also, I'll write 1997 and then shortcut is minus 2 to the power 1997, and the same way. So this is 1 and then minus 1. So it will be 2 to the power 1997 and then minus 2 to the power 1997. So all these terms, they'll be 0. So that is, this expression is clearly divisible by 1997. Now we'll take another question, which is find the fractional part of 7 to the power 100 upon 5, where these brackets, they represent fractional part function. Now I need to find fractional part of this expression. Now this 7 to the power 100, I have to check its divisibility with 5, and I have to find the remainder when this expression is divided by 5. Now I have to express this 7 to the power 100 as some multiple of 5. Now one of the way of doing it can be, I can write it as 5 plus 2 to the power 100. In that case, if I use the shortcut, I'll get the number as 2 to the power 100. Now dealing with 2 to the power 100 is little more complicated. So I look for something else. Now what I know is 7 square. Now 7 square is 49. 49 is 50 minus 1, and 50 is a multiple of 5, and I can deal with 1 or minus 1. So what I'll do is I'll express it as 7 square to the power 50, which is 49 to the power 50, and I can write it as 50 minus 1 to the power 50. So if I'll use the shortcut, I'll get it as minus 1 to the power 50, which is 1. So that is, when 7 to the power 100 is divided by 5, then this number, I can express it as some multiple of 5 and then plus 1. So if I'll divide by 5, I can write it as k plus 1 by 5. So in this case, the value of fractional part of 7 to the power 100 upon 5 will be simply 1 by 5, because 7 to the power 100 when divided by 5 leaves a remainder 1. So answer is 1 by 5. So let us take up another question, which is, if the units digit of 13 to the power n plus 7 to the power n minus 3 to the power n for n belongs to n is 7, then n is of the form. So we have to find the correct option. Now I know that I can find units digit by dividing any number by 10. So if I divide any number by 10, whatever remainder that I'll get should give me its units place. So what I'll do is I'll express this 13 as 10 plus 3 to the power n plus 7 to the power n minus 3 to the power n. Now if I'll use the shortcut, I'll get it as 3 to the power n plus 7 to the power n minus 3 to the power n. So I'll cancel. So I'll get some multiple of 10 and plus 7 to the power n. Now this multiple of 10, it doesn't change its units place. So I have to find the value of n so that its units place will be 7. Now what I know is 7 to the power 1 is 7, 7 to the power 2 is 49, 7 to the power 3 is 63, 7 to the power 4, 1, and then again after 4, it will be 7 to the power 5, which is 7, 7 to the power 6, 9, 7 to the power 7, 3. So if the units place for this number is 7, then n should be of the form 1, 5, which is 4k plus 1. So answer to this question simply will be n should be of the form 4k plus 1, where k is an integer. Find the units place of 53 to the power 53 minus 33 to the power 3, or I can say that find the remainder when this expression is divided by 10. And similar question can be, you'll find the fractional part of 53 to the power 53 minus 33 to the power 3 divided by 10. Now I'll start with this expression, which is 53 to the power 53 and minus 33 to the power 3. So since I'm looking for its units place or its divisibility by 10, I have to express it as a multiple of 10. So I'll write 5 into 10 plus 3 to the power 53 minus 3 into 10 plus 3 to the power 3. Now I'll use the shortcut, so I'll discard it. So I'll write 3 to the power 53 minus 3 to the power 3. Now we look at the pattern in the powers of 3. So 3 to the power 1 is simply 3. 3 square is 9. 3 cube, it's 27. 3 to the power 4 is 81. And thereafter, these values, they'll repeat. So if 3 is a multiple of 4, so if power is a multiple of 4, then I'll get 1. If it is of the form 4k plus 1, I'll get 3. 4k plus 2, 9. 4k plus 3, I'll get 7. And if it is of the form 4k, I'll get this value as 1. Now 3 to the power 53. Now 53 is 52 plus 1, and which is 4 into 13 and plus 1. So it is 4k plus 1. When it is 4k plus 1, the last digit or the units digit that I'll get here is 3. And then minus 3 to the power 3 is simply 7, which is 4k plus 3. 3 minus 7, which is minus 4. Now the first number is greater than the second number, so this value cannot be negative. Also, remainder should be positive. So when I'm discussing divisibility by 10, so the remainder that I'll get here is, so I should get a complementary number of minus 4. So there'll be 10 minus 4 and it is 6. So the units place of 53 to the power 53 minus 33 to the power 3 is simply 6. Or the remainder when this number is divided by 10 is 6. And if I have to find this fractional part, then this fractional part will be simply 6 by 10, which is 3 by 5. So that is the answer to this question. The problem is, let there be a function fn, which is 3 to the power 2n plus 3 to the power n plus 1, where n belongs to positive integers. Now it says we have to prove that f100 is divisible by 13. So I need to find f100, so which is 3 to the power 200, 3 to the power 100, and then plus 1. And then I'll have to prove that this number is divisible by 13. Now for divisibility by 13, I'll need to find some power of 3 which is closer to some multiple of 13. Now what I know is 13 into 2 is 26, and 26 is closer to 27, which is in fact 3 cube. So what I'll do is I'll need to express this 3 as some third power or a 3 to the power 3. So what I'll do is I can write it as 3 square into 3 to the power 198. I'll write it as 3 into 3 to the power 99 and then plus 1. So this is 9 and I'll write it as 3 cube to the power 66 and this is 3. 3 cube to the power 33 and then plus 1. So this is 9 and this is 27 to the power 66 and this is 27 to the power 33 and then plus 1. So I'll write this 27 as 2 into 13 plus 1, again 2 into 13 plus 1 to the power 33 and then plus 1. So because we are looking for divisibility by 13, so I'll discard this term. So I'll write 9, 1 to the power 66 using shortcut. So this is 3, 1 to the power 33 and then plus 1. So this is 9 plus 3 plus 1, which is again 13 and which is again divisible by 13. So this entire number f100 will be divisible by 13. So the question is 72C36 minus 1 and we have to prove that it is divided by 73. Now I'll start with 72C36 and we can write it as factorial 72, factorial 36 and factorial 36, and we know that any binomial coefficient is a positive integer, right? So 72C36 belongs to an integer. Now I'll write this 72 as 72 into 71 into 70 up to 37 and then I'll write it as factorial 36 and then factorial 36 and factorial 36. So I'll cancel this factorial 36 with it. So now what I'm left with is 72 into 71 into 70, and it continues up to 37, whole divided by factorial 36. Now I need to check divisibility by 73. So what I'll do is I'll write this 72 as 73 minus 1, 71 as 73 minus 2, and the same way I'll write 37 as 73 minus 36, whole divided by 36. Now recall the previous question where we have done this: x minus 1, x minus 2, and x minus n. So what is the constant term in this? So in this, the constant term was simply minus 1 into minus 2 into minus 3 into minus n, and all other terms, they were function of x, right? So I can write this as some function of 73 and then plus constant term. What is the constant term in this case? Constant term in this case will be minus 1 into minus 2 into minus 3, and it will continue up to minus 36, and that is factorial 36. So I'll write this as f73 upon factorial 36, and then plus, so minus 36 times, so there'll be plus, so there'll be factorial 36 upon factorial 36, so it'll cancel, so I'll get this as 1. So I'll take it on the left hand side. I write 72c36 minus 1 is equal to f73 upon factorial 36. Now 72c36 minus 1 is an integer, so right hand side is also an integer, and because it's a function of 73 and 73 is a prime number, so we can say that this expression 72c36 minus 1 is divisible by 73. So this is how we can prove this question. Now another way of solving the same question can be using Wilson's theorem. Now if you are comfortable with modulo functions, then you can use Wilson's theorem to prove the result.